Okay. Well, good morning. Yesterday we looked at molecular orbital theory. A raise of hands for people who saw molecular orbital theory for the first time yesterday. Good. And actually a small portion of the class. And a raise of hands for people who learned more about molecular orbital theory yesterday than they have before. That includes for everybody that saw it for the first time. That's everybody. That's great. Any confusions that linger with molecular orbital theory? Can we draw a structure using molecular orbital theory? Not easily. Probably not at all. Or if it is, it's like an abstract structure because you're looking at energy levels.
I guess I did have one question. So, would you recommend basically how the orbitals look and what their shape? Would you recommend memorizing those? Because I just remember going through active last night and they just had a picture of something that said based on this
what type of bond is present.
Yeah.
I would say you should recognize the type of orbital by its shape and shading.
Mm-hmm.
So you should be able to recognize a p orbital or a pi orbital. Mm-hmm. And you should recognize what types of orbitals overlap to lead to what types of bonding. So that question that you're asking about, I think, is actually more of a valence bond theory question, where it showed an atom, two atoms, and it showed p orbitals that were overlapping with each other, or at least next to each other. And so that was looking at the atomic orbitals that the atoms had and what type of bond would be made. Because you can't easily show that same thing with a molecular orbital. I guess actually in some ways you can. I'm going to show you guys this link that I have on our Canvas homepage. Oops. If you come down to ChemTube 3D and you go to these organic molecules, not all of these reactions have them, but a lot of the reactions have animated molecular orbitals. And so you can see they don't give you all of the orbitals. Like we learned that as you keep adding orbitals, you just keep increasing the number and energy that they have. But what you are looking at is the reactive orbitals, the highest filled orbitals or the lowest unfilled orbitals. And you can see how those orbitals change over the course of the reaction too. So you wouldn't ever get a question like that on active that says what orbital are you seeing? Because it's a bit messy, yeah? But you will get some valence bond ones on active.
I just remember it was CH4, and I just went to one, but one portion of the CH bond, and then showed the.
So what orbitals constitute this bond?
Yeah, I can't remember the exact question, but yes.
Was it asking for polar or non-polar? And then I think he gave you a list of 10 shapes after that, these ones are all polar, and then it's not one of these shapes. It's.
No, I think it was talking about the sigma pi or sigma star pi star bond.
So it gave you something like CH4. I don't know why this one's not coming to my mind.
I can look.
And then it said this bond here is best described as.
Yes. Sorry.
That's okay. It is important to be able to see how to apply both valence bond theory and molecular orbital theory. So let's do that as a review from yesterday. How would valence bond theory describe this bond?
sp3 to s.
sp3 to s overlap. Because the hydrogen is sp3 hybridized, right? The hydrogen only has the s orbital. Oh, okay. So this actually feels like they are merging valence bond theory and molecular orbital theory almost to throw you off. I'll sketch that one up
Okay.
on the board. I can see why you thought that was CH4, but it's because they've highlighted one of the carbon atoms,
I thought it was kind of like.
but then
'cause
they
it blew it up,
ignored.
it pushed it over.
They ignored two of them.
Okay.
There are two atoms in there.
Okay.
How do we know our carbon is sp3 hybridized? It's got 4 different electron regions. And the S comes from the hydrogen. How would MO theory describe that bond? MO theory will not describe it as an overlap of sp3 and S. MO theory would describe it as constructive bonding, which means it's not going to be star, but will it be sigma or will it be pi? Sigma. Okay, so the question that Brett was looking at had something like this, and I'm going to have to try my artistic skills here. And the confusing thing is, it looks like they took that CH bond and just elongated it, but they're actually ignoring 2 carbon atoms that are here.
Okay.
If we drew this in bond line, it would look like this. A CH3, and then a C triple bond with an H on one side. Now, what type of orbitals do we see here? P orbitals. Are these hybridized orbitals? No. P orbitals are unhybridized orbitals. They're atomic orbitals. But then the question was, what type of bonding is seen here? And it said 1 sigma star, 1 pi star, and then maybe 2 pi or 2 pi star. I don't know. There were a lot of answers that were provided. Based on the orbitals, are we forming a sigma bond? P orbitals aren't involved in sigma bonding. P orbitals are involved in pi bonding. So we can rule out any of our options that show sigma. Talk to me about the phase of the orbitals. When these orbitals are summed together, because they're mathematical equations, is it constructive or destructive? It's constructive. So we can rule out anything that is star. Star orbitals are destructive interference. And am I looking at 1 pi bond or am I looking at 2 pi bonds? 2 p orbitals that are overlapping gives me 2 pi bonds. Yeah, I can see why that one is a bit weird. And to be fair, you won't see a question like that on the unit test or the exams. But that's one of the benefits of the homework, in my opinion, is that you can feel out different image structures, different ways that questions can be worded. But part of the reason I give you a unit test before I bring you to the midterm or the final is because I want you to see how I'm going to phrase those questions.
So I'm just trying to wrap my head around some of the vocabulary.
Mm-hmm.
So when we're saying something is hybridized, the hybridized thing is the atom, not the bond. Is that right? And then the bond is either sigma or pi. But the bond itself isn't hybridized. It's the nature of the bonds that hybridize the atom.
Yeah. So it's the orbital that is hybridized. And then the orbital causes bonding.
And that defines the atom as being hybridized.
That's right. So when an atom is hybridized, its orbitals are hybridized to that same extent. And then those orbitals are what constitute the bonding. So you describe a bond based on what orbitals are overlapping. And those are either hybridized orbitals or p orbitals. But that's the valence bond theory approach. which says that the carbon atom keeps its own atomic orbitals. And the molecular orbital theory approach says carbon doesn't keep its orbitals. The whole molecule gets an orbital now. The people's orbital. Sounds communist. You guys have all seen a periodic table that is set up for electronegativities? What the heck? Never seen that. You guys seen something like this before? A periodic table of the elements, but it has electronegativity values put in it? Well, a lot of no's. 2D versions, that's fair. I have seen some 3D versions as well. Do you guys notice anything weird about this periodic table? Yeah, it's just rotated. If I flipped this back the other way, all the atoms would be in their appropriate spot, but written upside down. The reason that I want to show you guys this, the 3D tables that show electronegativity values often show fluorine with the highest column. Fluorine is the most electronegative atom. But electronegativity is a feature of pulling electrons towards yourself. Fluorine has the most number of protons in its nucleus with the least number of core electrons shielding the effect of those positive charges. So electronegativity is essentially the strength of electrostatic attraction, and fluorine's got the best electrostatic attractions. So when I see a periodic table that has fluorine at the highest and all of the other elements lower than it, it gives me the wrong idea of how fluorine interacts with electrons. So I brought this up last summer, and I told my students, I think it'd make more sense to have fluorine be the lowest because it's almost like a gravity well. If I put a marble anywhere on here, like an electron, then I can imagine where it's going to roll to. I can figure out which atom pulls the electrons similar to a gravitational pull. Jamie?
Would fluorine have the smallest radius then too? And like because of that, the electrons are just closer to the nucleus?
Well, those are two separate things, but that's true. You remember what makes up most of the size of an atom?
Is that it?
The electron cloud, yeah. So the atom that can pull electrons towards itself the most has the smallest atomic radius. So even though fluorine has more protons and neutrons than oxygen, nitrogen, and carbon, it is a smaller atom because it pulls in its valence electrons more.
But the noble gases, because we don't have a fuel valence. So how come fluorine is compared to small electronegativity?
Because the noble gases already have a stable valence shell, they have a filled octet, they are not hungry for more electrons. Whereas fluorine has one electron in its free atom state. Fluorine has one electron that is unpaired, and that unpaired electron is incredibly reactive, and fluorine has two core electrons shielding its nucleus, so it has a really strong pull on other atoms' electrons. I'm not sure if I did a good job of explaining that to you. So I had a student last summer who built this for me. I don't know how he did it. It must have been painstaking. But you can imagine you put a marble anywhere on here and it's going to roll down to a different atom with a higher electronegativity. That's the idea. Pick any of these two elements, put them next to each other, and you can see which element pulls electrons towards itself. But the problem with putting fluorine in the ground and everything else higher up is that fluorine would have been back here on a normal periodic table and you'd never see it. So he had to flip the table around in order to make it legible. Hayden?
Why should transition metals have higher electronegativity than metalloids?
Great question. I don't know.
It's tripping me out. Some of this stuff's not right.
And it is generally electronegativity increases up a row and across the column. But then there's some differences. You might notice that iodine and carbon have the same electronegativity. And yet, it wouldn't be hard to find a carbon-iodine bond labeled as partial positive on carbon, partial negative on iodine. What's that about? And if the carbon-iodine bond breaks, iodine is more likely to take the electrons with it than carbon is, even though they have the same electronegativity. So there's always exceptions to the rules, and transition metals are generally really big exceptions. One of the other exceptions you get with transition metals in Gen Chem is valence electrons and valence shells. Transition metals do some wild stuff with their valence electrons. So, electronegativity, big concept for us. We can abbreviate it as EN. And let's just make it as meaningful as possible and say that electronegativity is a pull on shared electrons. So we don't need to consider the electronegativity of ions. We don't need to consider the electronegativity, well, yeah, I guess just ions, something that's not sharing its electrons. We're going to keep this applied to covalent structures. The difference in electronegativity means that electrons are not evenly distributed, and this leads to polarity. Differences in electronegativity leads to polarity. Now, you have all learned about polarity at this point, but I know that polarity can be used outside of science as well, and so I really want to have this conversation again where we address what does polarity mean in your brain, even when you're not thinking about what it means in your brain, so that we can acknowledge it and then really make sure that we understand this definition. How do you guys use polarity or hear polarity used? Polar opposites. How about the North Pole and the South Pole? So, directionality. I like that.
Sometimes Republican versus Democrat.
Absolutely, right? A polarized political spectrum.
I just think of it like tug of war.
A tug of war. And one side wins, or is there sometimes an equilibrium between them?
I'll be above it.
Yeah.
With water, you could polarize water.
Oh yeah. Polarity being polar things are soluble in other polar things, like polar things are soluble in water. Great. So when we talk about polarity, we're going to put a positive and a negative, but not a formal charge. Not a true positive, not a true negative. Instead, we're going to do this partial positive and partial negative. And this is a lowercase delta, indicating partial. So what is partial charge trying to say? I'm not a fast runner. And Russ might be a fast runner. I'm not sure. Be fast.
Used to be.
But Russ is faster than I am. So Russ is partial positive with running, and I'm partial negative with running. Neither of us are actually as fast as someone who will go to the Olympics. We're not actually fast. It's not actually positive. It's not actually negative. It's just comparative to one another. There is a difference in this. Now, I have a problem with the larger scientific community labeling bonds as polar or nonpolar based on specific differences in electronegativity. The reason being, very few bonds do not have a partial positive or a partial negative. And those bonds would be things like pure bonds. Oxygen to oxygen, hydrogen to hydrogen, carbon to carbon. There's no difference in electronegativity. No atom pulls on the electrons more than the other. And so there is no partial positive. But then we have nonpolar bonds. And pure bonds are nonpolar, but not all nonpolar bonds are actually nonpolar. So some examples here would be the borane-hydrogen bonds. I know you guys maybe haven't worked a lot with borane before, but it will be a reagent we'll use this. Sorry, I'm calling it borane because that's the reagent we use. We'll work with boron this semester as one of our reagents. Another one that we'll use that's nonpolar is the CH bond. And these are called nonpolar, but they have a difference in electronegativity. And the partial charges that they get are actually able to predict how the reactivity occurs. For instance, when a carbon-hydrogen bond breaks, one atom has to take the electrons, the other atom loses them. Which atom do you suspect would take the electrons? Why? It's nonpolar. Shouldn't it just be a 50-50 toss-up? No. We know that hydrogen is less electronegative than carbon. So we know that there's actually a small partial negative on carbon and a small partial positive on hydrogen. So we call it nonpolar, but is it actually without poles? No, I hate it. Sorry, I'll die on that hill too. Tell me about the boron to hydrogen bond. Which atom would be more negative than the other? Look at the table. Don't guess. Which of them has a higher electronegativity value? Hydrogen. By 0.1, yes, but your textbooks will tell you that 0.1 difference in electronegativity results in predictable chemistry. And we can actually use it to create structures, to do a synthesis in organic chemistry that puts our new bonds exactly where we want it to be. So this is a partial negative hydrogen and a partial positive boron. That's wild. It's rare that hydrogen is the more negative atom. Last week, we also looked at sodium hydride, NaH. And we said that was Na plus, H minus. And we can see why. If I have electrons on sodium, and then I push it next to hydrogen, where are those electrons going to go? They're going to go to the hydrogen. So hydrogen, with just a proton in its nucleus, I don't even think you can call that a nucleus. It is just a proton. It has a better pull on electrons than many of the metals. Okay, what's the other type of bond? Polar bonds. So some of the most common ones for us. Let's look at, this is organic chemistry, so we should consider hydrocarbons and the bonds that they have. So let's look at the bonds that hydrogen makes. Let's look at the HCl, HBr, HI, HN, HO, HS. Those are some of the most common bonds we'll see this semester. We've already looked at the CH bond. So that's hydro of the hydrocarbon. Let's consider the bonds that carbon is going to make this semester as well. like the CCl bond, the CBr bond, the CI bond, the CN, the CO, the CS. And while we're at it, let's step this up and just show what happens when we have triple bonds and double bonds to these structures. Hydrogen can't have anything more than just that one bond. Now, once you've copied down my slanted list, take a minute to start writing in the predicted partial charges. Use this periodic table. It's not posted yet, but I think I can upload it. But I need your pen again.
I have a bunch.
No, really, I don't need it. Just needed it for that 1 second. I suspect a lot of you are making good progress. So in 30 seconds, I'm going to have you start working with each other. So try to get as many as you can in that time.
If they have the same electronegativity, is that just would that be considered like the pure bond?
Which is nonpolar. Yeah. So really, all pure bonds are nonpolar bonds. But not all nonpolar bonds are pure.
Mm-hmm.
So you can have pure bonds that aren't the exact same.
No. No, I think by definition, a pure bond
Has to.
is atoms of the same element. But I think what you're saying is if bonds don't have a big enough difference in electronegativity, yeah. And there's a couple of interesting ones that we'll talk about. A couple of interesting ones on this list that I have put as polar. But it's just to give you a mind frame and less to test you on. All right, work with one another to see if you agree. Where are the partial charges? Are there any deviations or are they pretty standard?
I can
As long
discuss
as
it.
if they're the same, you answer that. That's what next.
Yeah, we
Yeah,
could just said it like if they're like C and S, for example, if they're both 2.5, so that would be like a non-polar pure bond. So I
But
think
it
what
can't
he
be
was saying.
pure because it has to be the same, right?
Right.
That's what I was asking.
Right.
So C and S is non-polar, but you can't call it pure because it's not the exact same.
Yeah.
Okay.
Okay.
That's what I was asking.
Yeah, you know what? I didn't notice that actually.
That's what I was asking that I was
Yeah.
clearing.
I thought you were talking about the CI bond.
Well, I mean, it's the exact same situation.
Yep.
They are all 2.5.
Yep.
But pure by definition means it has the same things.
Yeah. That's my understanding.
I see the mind frame, but it definitely belongs in the
10 seconds.
carbon dioxide, you run charges.
So CL is -2 charge.
I didn't do them all. I just did like every.
Why did you put carbon and bromine?
Well, the one that's,
How does-
the one that's higher would be the more negative,
Carbon and iodine, carbon and sulfur.
the higher value.
That was my next question too. And I guess because since I mean bromine and iodine halogens, they want the electrons more. And I guess sulfur's kind of wants it more, I guess, for its shell. But like
It's weird, right?
yeah.
All right, guys, so some of you have pointed out some oddities on this list. I've put this list as polar bonds because I think it's a useful way to think about their reactivity. But some of you have noticed, looking at this table, they are not all polar bonds. Let's start with the bonds to hydrogen, where everything is actually polar. What charge does hydrogen have in each of these bonds? Partial positive. There's no exception here. Partial positive on every hydrogen. What that means is hydrogen is likely to pull negatively charged things towards itself. It also means that the other atom is likely to take the electrons in the event that that bond breaks. In fact, the reason that it's partially negative is because it already owns the electrons. I have had students in the past say, if it's partially negative, shouldn't it be repelled by a negative charge? Why would it accept electrons? Shouldn't it push electrons away? I get it. But this is the mindset I have. The reason it's partially negative is because it already owns those electrons. So yeah, if that bond breaks, it keeps them. It owns them anyways. It's partially negative. Now with carbon, we have some that we can easily go in and label as polar. What charge, partial charge, did carbon have in each of these? Carbon was partial positive in everything. And I'll put the ones that we know for sure. Carbon to chlorine, carbon to nitrogen, carbon to oxygen. What about in my carbon-oxygen double bond? Does that change anything? No, it's still a partial positive. And what about my carbon-nitrogen double bond? Carbon-nitrogen triple bond? It's still losing the electrons to those other atoms. So that makes chlorine partial negative, nitrogen is partial negative, oxygen is partial negative. Now, we can predict some reactivity about carbon and sulfur. Generally, sulfur holds on to those electrons better. So it's obviously not because of its electronegativity. What else does sulfur have that's different from carbon? It does have a different number of valence electrons, but it's not that.
It's more below the electronegative scale. That's absolutely.
Well, they've got the same electronegativity value. So in terms of electronegativity, they're the same.
Different specific terminology, but some of how it holds impacts a lot, right? And as you go down, it holds on them tighter.
Effective nuclear charge
Yes, that's
is, I think that's actually the opposite, where the effective nuclear charge weakens as you go down a row. No, actually, sorry, as you go across a row.
right.
In a column, effective nuclear charge is usually the same. But the reason an atom is larger as it goes down is because those valence electrons keep getting packed further and further away.
I mean, wouldn't sulfur, bromine, and iodine all have smaller radii and more shielding than carbon? So why would they want those electrons more?
They have larger atom sizes.
That's what I meant.
So why would they want them more?
Yeah, if sulfur, bromine, and iodine have larger radius and they have more shielding, why would the nucleus want the electron more?
Polarizability. As an atom gets larger, its ability to take even a neutral amount of electrons to its protons, it can take those electrons and distribute them in such a way that it creates partial negatives and partial positives. So iodine, or let me say iodide, the I- ion, is a very large ion, especially in comparison to the fluoride ion. There is a net negative charge on both of these ions, but iodide, being so much larger, can actually concentrate all of its electrons in one area and create a partial negative region and a partial positive region, which is not to say that iodide is positive. This is not to say that the bond is negative or positive either. Iodide is negative, but it can have a region that is more positive and a region that is less positive, a region that is more electron dense, a region that is less. Fluoride, being much smaller, is really not able to distribute its electrons as efficiently to create this temporary dipole. So larger atoms are more polarizable. If you give them a negative charge, they can actually distribute that negative charge more easily. We were talking yesterday about resonance and how delocalizing a charge makes it essentially a weaker magnet. Where is that charge? It's not in one place or another. It's spread out all over the place. Similar thing with polarizability. I've got a negative charge over a much larger area, and it can be kind of disrupted with this ability to polarize itself. So this is why it can be useful, even though these bonds down here don't agree with our differences in electronegativity. It can still be incredibly useful to say that carbon is partial positive to all of these, because when the electrons come to those larger atoms, they've got more area to be in, they've got a larger orbital, so it seems like the electrons are around that atom a greater portion of the time. Fluorine, or I guess we don't use the fluorine atom a lot in OChem, so that's why I didn't put it on this list. Chlorine pulls on those atoms really strongly. Excuse me, chlorine pulls on those electrons really strongly. Iodine, on the other hand, has just a huge orbital, so the electrons are just more likely to be found over there. You guys okay with this? It's a little bit uncomfortable to say that we've got these partial charges, but these partial charges are what agree with the chemistry throughout the semester.
Are these the charges that we're talking about with the van der Waals forces?
Yes and no. Some of these charges, especially the ones that are true dipoles, they are responsible for dipole-dipole interactions. Van der Waals generally is considered when you have like a non-polar interaction. Van der Waals is like the fact that electrons are always moving. You create temporary, instantaneous dipoles for a second, and then they disappear. But in that second, they allow for these attractions between molecules.
So this is technically a little bit more permanent than a van der Waals force would be.
That's right. Yeah. But actually, all of those forces are just magnetic interactions. Some are just weakly magnetic interactions, and some are really strong magnetic interactions. They're the electrostatic attraction. Now, there is another type of bond, and that's the ionic bond. And it is interesting in organic chemistry to compare a couple of ionic bonds. So the definition that the larger scientific community has set in place is that a difference in electronegativity of 0.4 or less is nonpolar, which is why the carbon-hydrogen bond at 0.4 is nonpolar. Carbon-bromine at 0.3 would be considered nonpolar. But then we've got some interesting ones. So we've already looked at the oxygen to sodium ionic bond. Oxygen has an electronegativity of 3.5, sodium 0.9. Their electronegativity is greater than 1. That's what distinguishes polar from ionic. But then there's a couple of other ones, because we also said ionic bonds are a metal and a nonmetal. So let's consider this one. This carbon to sodium bond. Sodium's at 0.9, carbon at 0.5. Boy, I'm really pushing myself to do this now. 1.6. Yeah. The difference in electronegativity is 1.6. So, ionic. It's categorized as larger than 1.0, so it's an ionic bond. But let's switch this up a little bit. I'm going to show a CH3, and then I'm going to show let's do lithium. No, we're going to do magnesium. And this magnesium will be balanced by something else as well, but we don't have to worry about that just yet. So carbon-magnesium bond, 1.2 to 2.5. That gives me a difference of I don't know. My math is really going slow in my head. 1.3. Okay, so also ionic, yeah? The interesting thing is that if you study the behavior of some of these carbon-metal bonds, they behave a bit covalent too. They have properties that bridge ionic to covalent. All of that to say, we have decided to put these descriptive labels. Nonpolar, polar, ionic. It doesn't mean that it really agrees with what we can predict from these molecules, because we can still get a lot of information about partial charges and stuff like that. All right, so we've got dipoles. What we need to do now is scale this up from a bond to a molecule. Here's the rule that I like to use to remember this. All polar molecules have polar bonds. But not all molecules with polar bonds are polar. Does that make sense? You guys agree with it? In order for a molecule to be polar, in order for it to have a molecular dipole, it has to have polar bonds. There has to be at least one region in the molecule where there is a difference in electronegativity creating these partial charges. But that doesn't mean that every molecule that has polar bonds has an overall molecular dipole. So let's look at this series. CH4, CH3Cl, CH2Cl2, CHCl3, and CCl4. The first compound, CH4, does it have polar bonds? None. I mean, yeah, its bonds have a difference in electronegativity, but we have rigorously decided that that difference in electronegativity is considered nonpolar. So none of the bonds have dipoles. Can the molecule have a dipole? No. So this is a nonpolar molecule. There's one other compound on here that is nonpolar. CCl4. All of these bonds are the same. So whether they're polar or not, the molecule at large doesn't have one region that's more electron dense and one region that's more electron deficient. But then throughout, I have polar bonds, and not all of my bonds are the same. So then these all become polar molecules. Jamie?
What like H2O versus CO2 be a good example?
Yeah, that is a good example.
Because I mean, the lone pair of oxygen is going to push down the hydrogens, making it so the partial positive charges don't cancel out.
Absolutely. So you've got this idea that CO2 has polar bonds, but it doesn't, it's not a polar molecule. In general chemistry, one of the tips that I give my students is if an atom's electron geometry agrees with its molecular geometry, which is a fancy way of saying if an atom has no lone pairs, and all of its bonds are the same, then that atom or that molecule is probably non-polar. If it has no lone pairs and all the bonds are the same, it's non-polar. That's what we've got in these two cases. No lone pairs on those carbons, all of the bonds are the same, non-polar. It works really well when we get heteroatoms as well. Heteroatoms like nitrogen and oxygen and the halogens, they almost always result in dipoles. So I want to give you guys some organic bond line structures, and I want you to decide whether these are polar or non-polar. And if they are polar or non-polar, can you point out regions in the polar molecule that where an atom is partial negative and where an atom is partial positive? I'm going to give a couple more. I know this process starts by drawing down these molecules before you can even start trying to rationalize their polarity. But there is a benefit from drawing down all these molecules. You're getting in the habit of drawing molecules, which you'll have to do all semester long. Now here's what I want to do. I want to give you guys some time to work with one another on assigning these polar or non-polar molecules. And I want to give you a chance to get up and move around and stretch. So we're going to come back right at 11 in 9 minutes. Use those 9 minutes to move around, get your blood flowing again, and use those 9 minutes to discuss with your neighbors about your assignments here on polarity.
I like it, that looks like a spider to me.
Yeah.
Well, because we've got the C's showing, but then we don't have the H's.
So it'd be C6. So each 14 bonds.
I just thinking about some biology.
Just for
Saturated
practice,
with
oxygen.
Yeah.
And wasn't that not?
That's it.
I can't.
And the lone pairs on the oxygen on the very bottom one. That's gonna explore it. It's gonna have this.
I think that was.
Yeah.
It's like water.
It's almost exactly like water, except
So we got
no
pure
hydrogen.
and then the non.
Are you in the lab,
So
James?
one's non.
Next semester? You'll use this solvent today,
Everything would be.
and
Yeah, because C
like
and the
another
H
12
bond
times throughout the
is
semester.
non-pure, and then the CPC is pure.
I think it goes.
Non-polar on the first
What?
Maybe I'm saying non-polar.
Yeah.
I did put a partial negative, but I wasn't sure.
What?
Nothing.
It says wrong.
You just don't know what one you're talking about.
Let's talk about the very first exact line.
Ah.
Like at the bottom of the.
Yeah.
Ooh, okay.
So the second one would be.
You have your.
Are you going down or?
Down. Same.
Yeah, it's gonna.
That would be
So like.
C6H12 because of the oxygen.
Because it has two electrons, like it's like your oxygen's here, your electrons here and here. And that would cause it to bend.
Yeah.
Or C6.
Like slightly. Like a smaller angle. So it'll be, yeah, it's like a slight negative here and then like 10 away. Oh. And then I thought like the one was next to
Or it would be polar.
yeah. That's what I thought. And then yeah, I agree. That this
Because
is
it's not.
not polar, it's like the same as the first one.
Oxygen is way different. Yeah, it's one different, so I don't think that this region is polar. And then the rest of it's non.
One thing I would like to see with the hetero
I just keep going back to biology.
need them
That's where my brain is.
show the bonds going to the when you show me this, I count 5 carbons, and then you do it.
Someone else is like, oh,
Same thing here, you've got 5 carbons, and you've got beautiful. That's it. So, I didn't hear your justification. Yeah, in the rate. Yeah, we've got 3 more carbons that come off.
So the first one, bottom one, yeah, would also be polar. And then just because oxygen's
yeah, like those
just
type
not
of
good,
shapes fit together. Yeah.
satisfied or however you want to say it.
No heteroatoms, so you can pretty much say non-polar.
That's
The NH one. And there's a difference of 1.1 there. So that'd be. That'd make it ionic.
This one is.
But the lone pairs do affect it, so the bond angle isn't 120. Oh, yeah,
Yeah.
yeah,
You don't have to show the bond.
yeah.
Like you can see, I just kind of wrote H next to it. That's one of the
Okay,
reasons.
so that one would be
You don't have to show these.
all carbons and hydrogen.
Well,
It's like
you have to show all the hydrogens on heteroatoms.
I feel like that
So I
one
know
would be
there are no hydrogens there. There are no hydrogens.
slightly.
because everything's just satisfied.
It's not wrong.
Because like, is that the? Am I thinking about it the right way?
Like you will
Usually
notice.
when I think about polar and non-polar, it like depends on like the like if they're on
Yeah,
the
he's
or
onto
not.
something that
Like
if
if like
you
oxygen
do
is
for
there, for
example,
example, so
carbons
it's like
opposites
it's
change.
one of the electrons or
Yeah.
Non-polar.
stronger stuff is yeah.
So,
I don't know.
where are the
I don't
options?
know either.
Or
We'll
because of
see
that.
if we're right or not, I guess.
And I'll talk about that. That if you
Yeah, just try to picture that in my brain. It's
like have two very different regions, you'll get an empty.
I bought one of the little modeling kits because
That never sounds right. But it can be both attractive to polar things and not. You can't. Or, you know, we went through that whole list of things that constitute a polar bond. And if you see that in there, and if it's not all of the bonds are the same, then you can pretty well say it is a polar bond.
I like don't see it.
Totally. Yeah. If you need to.
Yeah.
It can take more time,
I just imagine that.
but early on, that's a good way to practice it and find the skill.
I don't think that.
Okay, guys, just a couple of minutes. So if you need to still go move your legs, now's the time. Mm-hmm. Yeah. Yeah. You know, it's not wrong, but this is.
That would imply
It would imply it if you forgot about its geometry. So this oxygen has 4 electron regions, and it is sp3 hybridized, which means that these are not linearly across from each other, and these are not linearly across from each other, and certainly all 4 things are not sitting in the same plane. Which is actually saying still true here, because you drew it on a flat piece of paper.
Yeah.
It looks like all 4 things are in the same plane. So you do have to apply the geometry, even if you don't show the geometry. So there's nothing wrong with this, because we are open to those assumptions.
I know. I was trying to
Count its electron regions, now you know its geometry. It's sp3, it's got a tetrahedral geometry. That means that it is existing 3-dimensional.
You saved this last one.
The other thing, this idea I gave you that for any central atom, if it has a lone pair, it's probably holding. And oxygen has 2 lone pairs. So the oxygen is probably holding. But there's a lot of central atoms. This is a central atom, this is a central atom. And then you have to see how all of those central atoms combine. So there's a dipole moment from carbon to oxygen, and this carbon to oxygen. And the way that you've drawn it, it looks like those dipole moments completely cancel each other out. But because we know how it exists in 3-dimensional space, we know they can't.
Okay, you're right. Yeah, I forgot I had done that.
It's rare that they would cancel each other out, quite honestly. Unless it's truly linear. If you have like a metal atom, you can put a lone pair above and below, and then you can have things that are in the they're in a plane in a square orientation. We call it square plane. And that's still like yeah. Yeah. Oh well, this is only 2-dimensional. It exists in this plane.
What you create.
And then these are sitting above and below the metal. So yeah, it gets more complicated. But for organic chemistry, honestly, 9 times out of 10, you see a hetero atom, there's a polar moment. All right, guys, let's see what you got here.
Yeah, that's true.
No.
Structure number 1. Non-polar? Raise the hands. Great. So, we know that the bonds that constitute this molecule are carbon-carbon single bonds, pure bonds, and carbon-hydrogen bonds, non-polar bonds. But even when you consider that they are non-polar bonds, it is the same bond all the way across. So even if they were polar, for instance, swap out every hydrogen with chlorine or fluorine, it's a non-polar compound because all bonds are the same. Second structure, polar or non-polar. Polar, and I did have one person that said, maybe a little bit debatable, definitely partially polar, maybe slightly non-polar as well, because I've got this carbon chain over here that has no polarity going on. And imagine if that carbon chain extended. How far could it go before I'm able to stop saying the molecule is polar and start saying the molecule is non-polar? Next structure, polar. One thing that we can say is if there is a heteroatom, it's probably a polar compound, or at the very least, that it has some polarity going on in that region. This cyclic structure with nitrogen, polar. It's got another heteroatom, so it's going to have a dipole moment from the carbons to nitrogen and from the hydrogen to nitrogen. The last structure, non-polar. This is strictly a hydrocarbon. It has nothing but hydrogen and carbon bonds. Now let's see if we can apply the partial charges. No partial charges to apply in our nonpolar compounds. Where might I find partial charges here? What charge on oxygen? What's balancing that partial negative? The carbon with the partial positive. Good. What about down here? Partial charges. Oxygen takes a partial negative, and both carbons take a partial positive. What about with my cyclic nitrogen structure? Nitrogen takes partial negative, and, oh, sorry, I drew that as a partial positive. And just the carbons take on partial positive, right? Nothing else?
Just the ones with like.
Just the ones bonded to it. But does anything else, or is it just those carbons? Hydrogen takes on a partial positive as well. In fact, if anything, hydrogen takes on a larger partial positive than the carbons do, because there is a greater difference in electronegativity between that nitrogen and hydrogen. All right, Maddie.
For the bottom left one, I drew it out as like the Lewis structure, and it looked kind of symmetrical, but I'm curious, like with the oxygen, is it, it's tetrahedral, but with the lone pairs, they're pushing slightly more, so it's not like a true.
That's true, that it's not 109.5 degree angles, it's more like 105. But it's still very, very much tetrahedral, very far from being linear. So we had this CO2 molecule, and CO2 is strictly linear. But this structure, if you tried to do something like this, and you draw it as linear, you're allowed to do that with Lewis dot structures. But you have to be able to apply its geometry as well, if you make that assumption. So here it kind of looks like these dipoles are equal and opposite, just like how these dipoles are equal and opposite, resulting in no molecular dipole. But this is not really its true orientation. Instead, one of those lone pairs might come out of the plane of the board towards us. One of those lone pairs goes into the plane of the board, and then we can show those carbons being the plane of the board. And now I've got a net dipole. The two carbons kind of sum together to give us that. I was mentioning some molecules have this split between what they can interact with. Anybody know what this molecule is? I guessed at the number of carbons, to be quite honest, but this might be something that you find in your soap. Soap has this ionic region, very polar, interacts really well with water. And then it's got this huge carbon chain, oftentimes 13 or more carbons. And that is extremely nonpolar. So this molecule would be able to interact well with compounds like this on its nonpolar end. It'd be able to interact well with compounds like this on its polar end. And it'd be able to interact well with water on that polar end too. And this is that basis of how soaps work. It's also very similar to how your cells work. But instead of this CO2 minus group, your cells end with a PO3 2 minus group. And then you've got this positive interaction between those polar regions, positive interaction between those nonpolar regions, and they create that wall. All right. Feeling okay on looking at an organic molecule and determining where the polarity is? Wonderful. Now we're going to look at how polarity leads to intermolecular forces. We call intermolecular forces IMFs. The first force is felt by everything. It is a force that essentially results from everything being made up of charged particles. It is the bare minimum electrostatic interaction force. And it goes by like 3 or 4 names. I think the best name is the induced dipole or the dispersion force. But it is also called London dispersion, and it's called van der Waals force. London is not named after the city, it's named after a scientist, and van der Waals named after a scientist. And throughout the semester, you will hear me bitch and moan a lot about naming things after scientists. I just don't think it conveys science. But dispersion, an induced dipole, that explains what causes the force. Everything experiences this force. But it is incredibly weak. Lastly, it increases with size and surface area. You might feel like size and surface area are kind of the same thing. They're not quite. Take, for example, methane. Methane is natural gas, so obviously at room temperature and pressure, it's a gas. The dispersion forces that are felt between 2 molecules of methane are not very strong. So just having the kinetic energy that you have at room temperature and pressure, molecules of methane can easily overcome the dispersion attractive force. They don't interact with one another. Compare this to octane. Octane at room temperature and pressure is a liquid. It also only experiences dispersion forces to other molecules, but because it's much larger, it has more interactions. And so at the same amount of kinetic energy, at room temperature, everything has the same amount of kinetic energy. For the same amount of kinetic energy, methane can overcome the dispersion force. Octane cannot overcome the dispersion force. So that's how it increases with size, which is also increasing with surface area. But I want to give you an example of how it increases with surface area without changing size. This is a 5-carbon chain, all attached in a row. But if we attach these atoms slightly differently, such that one carbon is at the center and the other 4 carbons are bonded to it, we haven't changed its size. It has the same chemical formula, but we have changed its surface area. Is it intuitive which of these structures has a larger surface area? Maddie? Which one has a larger surface area?
The one on the left.
Yeah? So, do you remember this example from when I taught you Gen Chem? I gave you the same structure. You don't remember that from almost a year ago? Come on. The one on the left has a larger surface area. And the way that I like to think about this is to compare it to a basketball. This structure on the right has a net spherical shape, similar to that of a basketball. And if I took a basketball and I cut it open and I stretched it out, then I could create kind of this, this rug from my basketball. And I have essentially increased the surface area because not only do I have the exterior of that basketball, but I now have the interior that is exposed to other molecules as well. So we call it better packing. It has a better ability to pack with other molecules next to itself, and that increases its surface area. Now I want to say that these are both gases at room temperature, which is not great. And I actually don't have the exact numbers on me, so are you guys okay if we just estimate here? What we're going to say is that this molecule has very weak interactions, and it boils, so its boiling point is about 5 degrees C. It boils at 5 degrees C. But this compound has even worse attractions, and it boils at negative 20 degrees C. All right, if you want to leave a blank and go in and look up these compounds later and get their real boiling points, I'm all for it. I'm sorry I'm not giving you a real number, but the idea is the same. This one turns into a gas at a much lower temperature because it doesn't need as much energy to escape that attractive force. This requires a slightly higher temperature because it has slightly stronger attractive forces between other molecules. All right, next, let's look at the next strongest force, which is the dipole-dipole force. This requires that a molecule has a permanent dipole.
I also have a quick question on that one. Aren't those both pentanes, but one's just very compact?
Yeah, so this is N-pentane, normal, and this is neopentane, or you could call it 2,2-dimethylpropane. So they have the same chemical formula, same molecular mass, but they're structurally connected differently.
Right, so it's like the more elongated horizontally, the stronger the force is, basically.
Exactly. We could essentially say branching decreases boiling point. Branching decreases intermolecular forces, whereas having a much longer chain increases forces, which increases the energy to separate them, increases the boiling point. So the only examples we'll consider here have permanent dipoles. That's what we'll need to look at. So why don't we try to compare, let's say, applies with permanent dipoles. which of these compounds experiences dipole-dipole attractions to its other neighboring molecules? Only the one on the right, only the one with the oxygen, because that one has has a heteroatom, has a dipole. No dispersion forces felt for this structure on the left. What about between these two compounds? One that has a CO double bond and one that has a CO double bond plus a halogen. Which of these experiences stronger intermolecular forces? I'm getting contradictions. Can I hear your reasoning?
I think when you mentioned earlier the halogen, it's more or less negative, so it's like a balance. So it sets it apart, and if it's involved, I think it cancels out.
It might cancel out the dipole. That's an interesting thought that we need to consider. Does the halogen cancel out the dipole of the CO double bond? I would say that the halogen creates an additional dipole moment. That's going to increase dipole-dipole attractions. So actually, more dipole moments, more interaction, higher boiling point. And we can say that a higher boiling point is due to stronger attractive forces between molecules. But you aren't wrong that at some point, as you keep adding dipole moments, they do start to kind of cancel each other out. We had that series of chemicals before, CH4, CHCl3, CH2Cl3. The strongest dipole in that series was CHCl3. CH3Cl. Having one chlorine created a very strong dipole. But if you have two chlorines, it actually weakens the overall molecular dipole. And as you add three, it has a much smaller molecular dipole. So it feels a little bit odd that sometimes increasing the number of dipoles cancel each other out. But 9 times out of 10, for most cases in organic chemistry, more regions that have dipoles are going to create better attractions between molecules. You guys know what's coming next? Hydrogen bonding. Now, hydrogen bonding is as much a bond as dipole-dipole forces are and van der Waals forces are. It is about 1/10 of the strength of a true covalent bond. So the energy that it takes to break a hydrogen bond is not comparable to the energy it takes to break a covalent bond. So it's a bit of a misnomer, but on the other hand, we've been saying everything is just electrostatic attractions. Everything is just a magnet. And this is not as strong of a magnetic attraction as a covalent bond. But it's a stronger magnetic attraction than dipole-dipole or dispersion forces. In fact, it is a subset of dipole-dipole. It requires having a fluorine, oxygen, or nitrogen in a compound that is bonded to a hydrogen. And that hydrogen then must interact with the lone pair on a fluorine, oxygen, or nitrogen. The reason I've drawn it this way with like all lines leading to that hydrogen is because it doesn't matter which combination you have. As long as a sample has one of these lone pairs and a hydrogen bonded to one of these atoms, you will see hydrogen bonding occur. Which of these compounds has hydrogen bonding as an intermolecular force? Not both? Both do. Where is the hydrogen bonding here? So the lone pair on the oxygen, yeah, with
that's one.
but none of the hydrogens, and there's a lot of hydrogens, none of the hydrogens are bonded to one of these three atoms. Correct? So a hydrogen that's bonded to carbon doesn't count as hydrogen bonding, or can't engage in hydrogen bonding. The dipole is just not strong enough. Here, I have a hydrogen bonded to one of my atoms, and then I have lone pairs on this oxygen and lone pairs on this oxygen that can do the trick. So this one experiences hydrogen bonding, this molecule does not. Maddie?
So, the hydrogen bonded to F or N and hydrogen attraction to the lone pair has to be within one molecule?
No, but what we're typically saying is within a sample of a molecule. And just for some context, right? Let's say we wanted to weigh out this molecule in lab. This molecule has a molecular weight of, I don't know, let's say like 68. And I want to get 1 mole of it. So I'm going to weigh out 68 grams of that compound. How many molecules do I now have? An absurdly large number of molecules. You might remember in Gen Chem 1, I told you that Avogadro's number is so large, it doesn't even apply to the stars in our galaxy. It doesn't apply to the number of stars in our galaxy and the neighboring million galaxies. Avogadro's number is so large, it only applies to things on the microscopic level. So here, I've got 600 million billion molecules, and they're interacting with one another. So you look at one compound written on the board, written on your notebook, you need to think about all of the neighboring compounds that it has. Is that okay?
Because I was thinking with the one on the left, it's got the lone pair, so if it were with the molecule on the right.
Correct.
Okay.
Correct. So there are ways that I phrase these questions to make sure that you don't avoid this or run into this problem. One thing that I can say is, what is the strongest type of intermolecular force that this molecule will have in a mixture with this molecule? And then we could say hydrogen bonding. But usually what I ask is, what is the strongest type of intermolecular force this compound has in a pure substance, or in a pure sample? Or, what is the strongest intermolecular force that is common between a pure sample of X and a pure sample of Y? And what would that be? What is the strongest intermolecular force common between a pure sample of this and a pure sample of this? Dipole-dipole. They both have dipole-dipole. One of them has a stronger force, but it's not common to both of them.
Okay.
Jamie, you had a question?
It kind of got covered.
All right. Aiden?
Is this covered on like the this week?
The unit test, we'll talk about intermolecular forces. Yep. And you guys see that to apply intermolecular forces, you've got to be able to identify polarity. And to identify polarity, you've got to be common with those electronegativity differences, so just what atoms result in polarity.
Did you already say is hydrogen bonding stronger than dipole?
It is stronger. Yep. So we went increasingly stronger.
Okay.
Dispersed is the weakest, dipole-dipole. Hydrogen bonding is a very narrow subset of dipole-dipole. It's the strongest types of dipole-dipole.
I think the subset maybe gives less. The word subset.
That's fair. Yeah, by subset, I just mean all hydrogen bonds are dipole-dipole interactions. It is the dipole-dipole that puts a partial positive on H, attracting it to the partial negative on an O, or F or H. Okay, so let's Let's do one more. In a pure sample of this substance, will it experience hydrogen bonding? And what type of hydrogen bond interactions are possible? It's the nitrogen bonded to hydrogen, and that hydrogen will be able to hydrogen bond with the lone pair on and the lone pair on nitrogen. So in a pure sample, hydrogen bonding could be the NH interacting with the lone pair on O, and it could be the NH interacting with the lone pair on N. Obviously not the same molecule. You would need two molecules to have that intermolecular attraction. All right. Clear as mud? What do you guys think? Intermolecular forces are not quite the same as reactivity, but intermolecular forces can lead to reactivity. If you have something that has a very large partial positive, like on these hydrogens, attached to a nitrogen or attached to an oxygen, then that can mean that the hydrogen can be easily taken away, because something else is going to be really strongly attracted to that partial positive and maybe use its electrons to bond to it and take it away. So we've looked at how to identify partial charges, how to identify intermolecular forces and polarity. But in our next class, we're going to look at our first type of reaction. We're going to look at acid-base reactions. And we're going to look at how electrons are exchanged, what atoms are allowed to do with their electrons, what atoms are not allowed to do with their electrons. And then we're going to see how having certain dipole moments in a molecule can make something a better acid or a better base. We're going to look at how having resonance in a molecule can make something a better acid or a worse base. And we're going to look at how electronegativity applies to acids and bases. So we're going to define our acids and bases, we're going to look at how the electrons move, and then we're going to learn an acronym that helps us predict reactivity. All right. You got a question?
You already answered it.
Yeah? Okay. As you leave today, here's what I would like you to do. I'd like you to look back at the notes that we've just covered and identify your muddiest point. What is the topic that we covered today that you feel like you are going to have to go back home and review? And I'm going to be standing by the door, so as you pass by the door, just tell me, I'm going to go home and review X. I'm going to go home and review Y. Deal? Okay.
How you would